All right, continuing on in this series on automating the crisp DM process. In the first video, we started with exploratory data analysis, aka the data understanding phase. And I began with creating a function that automatically generated all of the statistics, metrics, and visualizations we need for univariate analysis, meaning looking at one variable at a time. Now I want to shift to bivariate analyses, which is still part of the data understanding phase or exploratory data analysis, but it allows us to look at pairs of relationships. And it's not every relationship we're interested in. We're really just interested in each feature's relationship with the label. So we want to identify a Y or an outcome that we're interested in, and then we want to look at every single X or feature and how it relates to or affects and how reliable that effect is with the label. And this will help us to sort of understand, again, further information about how we might need to clean and prepare the data and what we can expect possibly when it comes time to model the data. So what I want to do is take you to a list of the things we want to generate. Now, this isn't an all-encompassing list. There are other ways you could customize this and make this even better. But in my book, I'm trying to introduce students to these concepts, and so I'm just beginning with the bare minimum exploratory sort of metrics and visualizations we want to look at. And I've divided up here based on the relationship type, whether it's numeric to numeric, numeric to categorical, or categorical to categorical. So on the right, this is the label or the outcome data type, and on the left, the input data type. Now, N to C, this counts for C to N as well, same thing either direction. Since it's pairs of relationships, we don't really care which direction that's in. We'll use the same tests and same visualizations. All right, so for statistics and measures, I'm going to assume you've got a stats background, and I don't have time to go into the details of all these. This is more of a reminder or summary. If both the feature and label are numeric, that's where we're interested in the linear regression equation, correlations. However, you might know that it depends on some assumptions. These Pearson correlation and the linear regression equation depends on the assumption of normality and a normal distribution. If it doesn't meet a normal distribution, we might need to, or if it has different data types, we might need to use different versions or different metrics of what I'll call effect size, or how much the feature predicts or is related to the label. The visualization we'll make is typically a scatter plot with some sort of trend line. In a numeric to categorical, we're going to look at a t-test or an ANOVA, depending on how many categorical values there are. If there's two groups, a t-test, or three or more, we'll use an ANOVA F. And then typically some sort of bar chart where each bar represents the mean value of each group, of each categorical group. Finally, with C to C, we'll use a chi-square test. Again, I'm going to assume you're somewhat familiar, or you could look these tests up to get more information on these. And we'll create some sort of crosstab with a heat map of how much each of these categorical relationships exist. The purpose of this video is simply to show you how to automate all of this into a single function so you no longer have to rewrite the code every single time for every single data set. So let's get started. I'm going to use 3 data sets. In the last video, I used these two, an insurance data set, an NBA salaries data set, but I'm going to add to it a categorical data set as well for airline satisfaction. So to get these, you can go to Kaggle for all of them. Go to sign up for an account. I just use my Gmail and my Google to log in. This one, U.S. health insurance data set, you can just go to Datasets and search for it. That's where I got the health insurance from. NBA salaries, it's for this particular season. This is where I got that one from. And finally, the Ames, Iowa housing. Oh, sorry. I meant to do, let me pull up. Let me go back to Datasets and search for, I meant to have airline satisfaction. I'm pretty sure it's this first one here. I can tell you very quickly. Yep, this is the one. Gender, customer type. And then this one has a simple satisfied or not satisfied. Come on, scroll. Let's try that. Oh, it's not showing. I've got to change this to all 25 columns. Apply. There we go. Now you'll get satisfaction at the very end of all this. They've got a bunch of stuff like their ratings on ease of booking, food and drink, the categorical feature we want to predict. There we go. Satisfied or not satisfied. Even if this one's not the exact one I have, it'll work just fine if you want to use that data set. All right, so let's dive in. and let's learn let's make a function to calculate all of these. So what we're going to need to do, we learned in the last video how to create a function, and we're going to want to iterate through every feature in the data set. We're also going to have to mark which one is the label when we call a function in order for this to work. And then finally, we're going to need some if statements that divide up based on data type of both the feature and the label. So it'll be a bit more complicated than our univariate stats, but not so bad we can't do this. So I'm going to read these in. I only printed out the airline ones so you can see what we're looking at. Looks like on mine I've got satisfaction listed first. But I want to begin by making our function. So I'm going to define a function. I'm going to call it bivariate, and I'll call this one just stats, bivariate stats. And we're going to have to pass in, we'd like to pass in any data frame. We want it to not matter what data frame goes in, but each data frame is going to have their own unique label. Therefore, we're also going to have to pass in the name of the label column in order to identify that. So that's why it's a little bit more complicated. Finally, I like to add a round to option and default it to something like 4, because a lot of the stats we're going to get back are going to have a ton of decimal places, and we often don't really want that. We'll let whoever calls a function overwrite that, but we'll default the function to 4 decimal places. There's our function. Let's go ahead and import all the packages we're going to need. We know we need to deal with pandas. To run these stats, I'm going to recommend we use the scipy function, but again, you can change this to whatever you'd like. So from scipy, import stats. And just like before, I want to make an output data frame to print out results in. So basically what I'm looking for, I'll show you up top here somewhere, is I'll show you the result we're going for is a function that will give us a list of features, and we're assuming we've already pointed out the label. So for example, in this one, the label's charges, and I want the features down the left. I've added in some other cleanliness properties we did in the prior video here because it's useful in some cases to understand. You'll see why later. But then I've got a list of metrics that apply to bivariate relationships. So for example, smoker, region, and sex, those are categorical values, and so I have an F score. Children, BMI, and age are numeric, so I have a linear regression equation and a Pearson correlation, but they all have a p-value that tells us how reliable that relationship is. And I sorted the table by p-value. I just want you to have the end in mind that we're trying to get to here. Here's an example of the airlines data set where that one, the outcome is satisfaction, it's categorical. And so we never have Pearson correlation or linear regression because the label is categorical. Instead, we have either an F score if the feature is numeric, or we have a chi-square score if it's categorical. But once again, we have a p-value regardless of what feature type it is. So this is what we're trying to create here. All right, back to the beginning. We've got an output data frame. I want to start with just the numeric to numeric condition. So let's handle that scenario, which means we're going to need a data frame that gives us all of the metrics that are required for numeric to numeric features. Let's make one for the linear regression equation, one for R. We could do R squared. I don't think it's that meaningful if we already have R, so I'm just going to ignore it. But we will want a p-value as well. So let's make 3 columns for those. All right. Equals, let's go to, I think I'm going to do the p-value first. And then let's do R. Then I'll do y equals mx plus b as the name of the column. And I'll call that good for now. So let's come down here. Now what we've got to do is loop through each of the features and grab just the numeric ones to calculate these results for. So I'm going to say for feature in df is what they pass in. If I just say in df, that'll work, but df.columns, that'll specifically return a list of columns. I just want you to see that this is what we'll get. It's the default property if we were just to say for feature in df or something like that. All right, now what we need is to check, first of all, make sure that we're only calculating these when both the label and the feature are numeric. All right, so to start, you might remember from the last video, we had an if statement. We were able to check a column to see if it was numeric or not using pd.api.types.isNumeric. Let's see if it pops up. dtype, there we go. And in here we have to pass in the entire column of data, which means we're not going to pass in feature. That's just the name of the feature. We're going to pass in the data frame with that feature name right there. In the last video I called it column. You can call this feature or column. The reason why I'm calling it feature is I want to differentiate it from the label, and they're both columns. But again, you'll see. You can call it whatever you'd like. So if that's numeric, I'm going to stop right there and just say if the feature is numeric, I'm going to assume for now only that I'm going to be passing in only numeric labels, and then we're going to modify this function a little bit at a time. But let's just start it in the simplest way possible. So if the feature is numeric, then we're going to want to calculate a p-value, an r, and the y equals mx plus b formula. You might remember if you're a student from a prior chapter or just from your own experience that we can get that using the stats.linRegress function. And for that function, we pass in, I'm actually just going to print this out so we can see it work and we can test as we go along. That function, we pass into it a column for the feature, which is going to be numeric. And then we pass in another column with the label. Where did this label come from? Remember, they're going to pass in the name of it when they call the function right here. So in this for loop, it's going to run this only if the feature is numeric, and it's going to run this against the label. So it's going to break if I don't pass in a label name that's also numeric. But don't worry, like I said, we're going to come back and modify that later. Okay, so let's just make this print out and call it good. I'm going to save that function in memory. We've already got the insurance data set in here and the NBA salaries. Let's run this through both of them really quick. So let's try Bivariate stats, and I'm going to pass in df insurance and see what we get. All right, missing, and I did this on purpose because I want you to see how this is different from our last function. Bivariate stats is missing one required positional argument label. So what that means is we told it needs 3 parameters passed in. On this one, the last one, round 2, this third one is an optional parameter because we already gave it a default value. They can leave, whoever calls this function can leave that off. But we can't leave label off because there's nothing we can default this to. We have no idea what data set might be thrown in here. So we just put in label to say, to force people, whenever we call this, we have to put in the name of a label. How does it know that df is supposed to be a data frame? It doesn't know it right here. It knows it right here when we try to iterate through it, and right here when we try to use the feature, and also here and here when we try to use the features. So down here, we're going to pass in the name of the label, just a string, which for the insurance data set we want to be charges, because we know that data set, we've used it before. If you're not sure, come up here, print out df insurance, and take a look at that if you didn't watch the prior video. All right, so let's pass it in with charges now. And we get 4 linear regression equations printed out. All right, what we've got here is slope, that's the m, intercept, that's the b, our r value, p value. They also give us the error term, standard error, and then even the intercepts error as well. So I don't think we want necessarily all those, but we're going to need to pull out at least some of these that we want to keep and put in to build out these tables here. This last one, the slope is 1, intercept is 0, r is, it's a perfect correlation of 1. Why is that? Well, print these out real quick. I'm going to print out the feature names along with each of these and run it again. So as it loops through each feature in the data frame, notice that it's only going to print if it finds one that's numeric. Age is numeric, and so we got a valid equation. Same with BMI, same with children. Oh, but look, it's also printing out the relationship between charges and charges. Last time through the loop, both of these are df charges. Yeah, that's kind of irrelevant. We don't care about the label's relationship with itself. I mean, we could just ignore that result and not worry about it. But if you're like me and a little OCD and you don't want it to print out garbage, I'm just going to say if feature not equals to the label, and then tab these in once again. So now it's only going to run those for anything but the label. That's better. Okay, so what I want to do is rather than just print out these results like before, in place of this print line, I want to insert a row into my output data frame, and I want to add a P and an R. Now in the last video, we made an index column called feature name. I'm just going to use the feature name as the index, and I'm not going to worry about creating a label for it. I don't know that it's that important. If you want to do, well, I'll show you what I mean here. Let's go ahead and change this. You might remember from the last video, we used, not df, output df.loc, and we can insert a row with the feature name there. And rather than print, we're just going to make a list. And I'm going to take this whole equation this time. I'm cutting it, not deleting it. And I'm going to store it in a variable. Now, I could store it into a single variable like results equals, and then I'd have to go and pick out each piece of the results like this. Results 0, that's the slope. So that's the M portion of this formula. The P is all the way, it's 0, 1, 2, 3. So I'd have to put results 3 to get the P value. Just watch me for a second because I'm going to show you what I think is a better way of doing this. And then I'd have to do results R is the 0, 1, 2. It's the second index position, or the 2 index. And then lastly, I'd have to build an F string out of putting together y equals and then add the slope and intercept. All right. I don't like creating one big object like that where I have to read into the indexes of it. What I'd prefer to do is store everything they give me in their own unique variable. For example, slope or M, I can just say M B is the intercept, R P M B R P, and then let's see, how many do I have? 1, 2, 3, 4, 5. Even the intercept. I'm not even going to use the standard error or the intercept. So I am going to, I'll just use error for the last one, and that'll actually give me 2 errors. So, yep, I'll leave it like that. So what this does is it automatically stores this kind of a tuple of results, kind of like a tuple dictionary. I forget what we call that. Anyway, it's going to store each of these within individual variables for me, rather than putting it in a big results block like this. So what it lets me do now is I can say, all right, the first one, P, I can just reference the P variable. Second one, R. Third one, I can build out my F string once again with y equals. Now I can put in M, X, plus B. I think I like spaces between those. Okay, that's it. There's my linear regression equation by using the variables I stored right here from the results of this function right there. So now that I have rows being inserted, let's formally return the output df just like we did in the last video and run this one more time. Okay, got my P and R, but look, it's in scientific notation because didn't I specify 4 digits to round to? Yeah, I did, but I'm not using this variable anywhere to actually round the results. To do that, I'd have to put it either around, oh no, I don't think I can put it there. I'd have to put it right here. So I'm going to use the round function and then input that round to variable right there so that anyone who calls this can specify or overwrite round to, and it'll automatically put that number right here and let them adjust how many decimals they want. So round 2, same thing on M and B. Okay, let's give that a try. Much better. That looks nice. I think I prefer spaces around all of this. Feel free to do it however you'd like there. Okay, cool. So we've got the relevant stats we need for each of these. Now, I think what I'd like to do is, for now, I think I want to sort the values by effect size. So when I return the output data frame, I'm going to sort values by R. and I want to do this from greatest to least. So ascending equals false. So I automatically get it back from the strongest correlation to the weakest correlation. So for these three variables, age has the biggest effect size on charges. So a 1 unit increase in age, 1 year older, means I cost an extra $257. Now, obviously, children's much bigger, but again, the reason why this one's larger but has a smaller correlation is because age and children are on a different scale. So we can't really compare. We can't compare this number and these numbers in the linear regression equation because they're on different scales. We compare them based on the correlation. Yeah, if they were standardized, we could, but that's enough for now. So we've got the start of a good bivariate stats function. However, if we were to run this on another data set that doesn't have a numeric label like df, actually, first of all, let's do our NBA. Check that one out. And let's predict, is it salaries? I can't remember what it's called in that one. I'd have to explore. No, I think it's salary. I better take a quick look here. So I'm going to print out df nba.head. All right, salary. Oh, capital S. That's what we needed. All right, perfect. Come down here. There we go. So this is what I want you to see. The advantage of making a function out of this is it didn't matter which data set I dropped in here, as long as I spelled my label right. It just automatically works. And in this one, we can see that when it comes to predicting NBA salary, it's the number of points per game that they score that has the largest effect on how much they get paid, followed by field goals taken. No. That's probably field goals made, and that's field goals attempted. I'd have to look that up, I guess. 2 points attempted. Hopefully, you understand your stats and you recognize there's a lot of intercorrelation among these. This is useful for exploring, but none of these are taking into account their intercorrelation with each other. So this is just a guide. It's just a starting place to understanding which things have the biggest effect. But it is helpful to see the signs on our linear regression equation. Each of these have positive effects. The older we get, the fatter, no, I shouldn't say fatter, the bigger we get, because it could be muscle. BMI is not a great metric. And the more children we have, that all increases how much our insurance costs. The more we score, the more we attempt shots, these all increase our salaries. Are any of them negative? Let's see. Oh, unnamed, which we don't care about. That was just a blank. That was just the row index. All right, but what do we have going on down here? So this is a case where we have missing data in some of these cells. And as a result, the SciPy function, this doesn't work when there's missing data. But let's address that at the end. Let's get this function working for all data types next, and then we'll worry about addressing cleanliness issues at the end. So what I want to do next is I'm actually going to skip from numeric to numeric all the way down to categorical relationships, because the categorical to numeric is a little more complicated, only because we need to handle both C to N and N to C. It's not that bad, but let's go down and do C to Cs and include that next, because right now we're not able to handle those at all. If I were to try and call this bivariate stats and pass in df airline and satisfaction. Oh, I always got to check up here. Make sure I get the label right. Satisfaction. Yeah. So this satisfied, make sure I spelled it right. We're going to get an error, or actually we'll just get nothing back because none of our relationships were C to N. Oh, there we go. It can't divide any of them. So in other words, up here in our function, there were features that were numeric, but we're not checking the label at all. And so basically, as soon as it tried to calculate one of these, it said, wait a minute, we can't do that with a categorical label, and it just broke. So let's handle this. Where do we want to handle this? Well, here's where we're checking if the feature is numeric, but technically we better make sure that both the feature and the label are numeric. So I'm going to add an and then change this to df label and say only run this if both the feature and the label are numeric. Next, I'm going to say elif not, let's say if one is not numeric, or no, we'll make this for, well, let's do this for both. How about, let's say if, I'll just copy this whole thing, and you know what, maybe we'll save this. This is our chi-square condition. This is if the feature is not numeric and the label's not numeric. Then this is where we'll process C2C relationships, and we can label all these process N-to-N relationships. Process C2C. And then that's kind of a simpler if statement. I like that because then we can just use an else down here. So maybe I lied and we're going to go ahead and do both C to N and N to C relationships right now. So this is then the condition we'll get if they're not both numeric or not both C to C. So we better do something here because we have to have something in the elif or else it'll give us an error here on the else. So if it's a C to C relationship, let's just simply put dashes in all of those blocks for now. So we're going to add the feature in there. And then, like we did in the first video, we're just going to put a list of dashes because it's currently not relevant. I think I like single quotes better. Not that it matters. No, I just got 3. All right, there we go. So, in fact, let's put this in for both just to make sure it's all working right now. And this is where we're going to process C to N and N to C relationships. Okay, so that should fix this. My return should be happy now. Yep, good. Oh, by the way, sort values, let's comment this line out because that will break. Now that we're putting in dashes temporarily, if it tries to sort on the correlation column, this one, we're going to get an error because it can't sort an object with the R correlations above. So I'm just going to change this to, we will, by the time when we're done, we'll sort by something else. Probably p-value would make more sense. But for now, let's just return the output data frame and make sure this works. There we go. So sex, smoker, and region, these are getting processed right here. And it's putting in dashes for those on NBA salary. Let's take a look. Okay, now it includes all these categorical variables. We still have these that have missing data. Why are those missing? Oh, I bet these are people who've never taken a field goal or 3-pointer or something like that. Anyway, and then airline satisfaction. This one now works, but it's returning nothing because satisfaction is categorical, and we're not doing anything with C to N or N to C. And so we're just getting dashes back for everything. But we've got the structure in place now. So the if block's in place. Now we just need to fill in the processing that needs to happen here. So let's go ahead and do C to N, since even though I said we're going to do it C to C. Let's start with this one here. Well, we need it to work whether the feature or the label are the categorical or numeric ones, but it is important that we put them in the right order. When we call the stats package and use the the ANOVA function, we do have to divide it up properly. So you know what we're going to have to do is we're going to have another if in here where we check and see which one is. We know that if it came in here, if it got to this else, we know that one of them is numeric and one of them is categorical. They're not both going to be the same. So how about we just check if one of them, the feature, for example, is numeric or not, and then that'll tell us whether to set the feature or the label as the number. Let me show you what I mean. Is numeric d types, and let's pass in df feature. So if the feature is numeric, then let's relabel them. The num is going to equal the feature name, and cat is going to equal the label name. Otherwise, it's the reverse. Num equals the label name, cat equals the feature name. Because you might remember from the book or from doing this on your own that we're going to need to, in order to use the SciPy's f function, the way it works is we're going to be calling stats.f one way, and we have to put in lists of numeric values like this. So, for example, on let's say we're looking at the relationship of gender on or satisfied to flight distance. What we need to do is we need to get a list of flight distances for all satisfied customers, and that goes in here. And then we need a separate list of flight distances for not satisfied customers, and that goes in here. So to get those lists, we're going to do some fancy, we're going to do some grouping, but it's important that we know which one is the feature and which one is the label. All right, we'll print these things out as we go along here. So let's do this. Let's to make this work, we're going to make a list of groups first of all. And the groups are going to be the unique value names of whichever one is the categorical feature. So we've fixed that. We've resolved which one is categorical right here. It can be either the feature or the label, but it'll be called cat when we're done. So I think you might still be a little confused unless I just go ahead and print out something like this. Cat is going to be cat, and num is going to be num, and I'm going to comment this out right here just so you can see how this is going to work. All right, so as it went through each of these, see how let's see, num is charges, cat is categorical is sex, smoker, and region. But down here when I run it for the airline, now it's switched it up. In here, the label is now satisfaction, which I specified as a label. That's now the categorical one each time, whereas it's the feature that is the numeric one each time. So it's flipped it in this one versus this one. This has always been the label, the numeric one up here. That's why we had to do this, is to make sure we specify which one is categorical and numeric. Anyway, now that we know that, we're going to, first of all, get a unique list of groups by simply going df cat, whichever one the categorical one is, dot unique. And just so you can always see what we're talking about, I'm just going to print that out. So that's all I've done, is I made a list here of all the group values. Now, I'm going to create a filtered list of each data frame. Sorry, a filtered list of numeric values for each one of these categories. So because I don't know how many categories there's going to be ahead of time, I'm going to have to do this dynamically in a loop. And then I'm going to add a big list, kind of this is the format it'll take. Numeric list 1, numeric list 2, numeric list 3. So I'm going to make a list of lists, and this is going to be a list of numbers for each one of those categorical values. So for sex, I'll get a list of charges for females that'll go right here, and a list of charges for males that'll go right here, and there won't be a third list because there's only 2 possible group values. But for region, there will actually be 4 sublists in the overall list. It will have numeric list 4 there when I make this one. So to do that, rather than print out groups here, I'm going to, first of all, I need to make my outer list. Group lists equals, this is the overall list, the one that will be right here and right here. And then I want to loop through each one of these unique values one at a time and grab the list of numbers from the data frame for that group and append them inside this list as these sublists. So to do that, I'm going to go for G in groups, group list. Honestly, maybe it's better to call it numeric list. It seems to make more sense to me. Whatever. You can name it either one. Nlist, glist equals. Hopefully remember how to filter a data frame. I'm going to say go to the data frame where the categorical column equals the group value that I'm currently on. So for G in groups, this is iterating through like female, male, yes, no, each one of these regions. So G, the first time through, is representing female. It's saying go into the data frame, and where the categorical value, which is going to be sex, where sex is female, that's what this is saying right here, where df sex equals female, return the entire list of numeric values. So this says go to the numeric column, which will be charges, and get a list of charges and store it here in nlist. Then all I have to do is say group lists dot append numeric list and put that in, or glist. Or you could have done this all in one line. We could just say group lists dot append, and that's the same thing. Let me save ourselves a line. So what's being returned here is a list of charges where sex equals female. That's what all this is representing. And it will go through for every value, every unique group value in the sex column, which is only 2. But because we have a for loop, it's now dynamic, and it'll work whether there's 2 values or whether there's 4 values or 400 values. Now that I have that, running stats one way is a lot simpler. I'm going to come here and say, I want to input each of those sublists right here. So the list of charges for female and the list of charges for male. The way I do that is I can just say group lists star. And it's such a great shortcut. It's just, oh no, I put the star up front. That says the star means what I see next is going to be a list of lists. And it's going to be the equivalent of this equals, actually I'll put a comment right here, same as group lists 0, group lists 1, group lists n. That's what that's what the star does, is it will break it out and input each sublist one at a time like that, which is exactly how this stats package one way works. So this will return it. Let's just print this out for now so you can see the results. Whoops. All right. Here's our F statistic for comparing male-female and the p-value. F-stat for comparing smoker, yes, no, and the p-value. Region, p-value. Perfect. Now all we got to do is insert this into this table. Where should we put it? Well, let's just add it. We've got a p location already. Let's just add an f here after the y equals mx plus b formula. So I'm going to come and say up at the top, add f. And then down here, let's store these results rather than print them. F, P, because it just gives me 2 values. Yep, F and P. Take off this extra parenthesis. And then when I input the results right here, instead of putting a dash, this is where the P value goes in the first spot. I'm just going to go ahead and put the variable P, which we just created right here. And then I'll put the F at the end. Whoops. Right there. Okay, I think we're good. Let's give this a try. Run that. Oops. All right, so it says that I've got mismatched columns, which means I'm trying to input 4 values right here. In fact, let's double check our, let's follow this. So it's happening, oh yeah, here we go. First of all, we call the function, and then down here it's running line 12. So this isn't the problem. What's happening is here on line 15 and 12, we created a 4th column to handle F, but it still needs to know what to put in for that F position here when we have an N-to-N or C-to-C relationship. So right here, notice we're only putting in 3 dashes. We need to add a 4th dash. And I'm going to leave this bug in the video just because I want you to get used to seeing how to interpret errors and then see my process for following through and understanding the output here so that I can fix them. Anyway, put that in, and then right here we've got a P, an R, and then the formula. There's still only 3 values right there, even though it looks kind of complicated. Only 3 values going in. So I'm going to add one more comma and just put a dash because there is no F statistic here in an end-to-end relationship. Also, that reminds me though, I got to add my rounding, just like I have right here. I'm going to round around the P and the F. Round, whoops. Okay, let's run that now, put it in memory, run our function again. Here we go. Now we have, this works for every feature in the insurance data set because everything's either an N-to-N or a C-to-N relationship. We get a correlation when it's numeric, N-to-N, and then we get a, we still get a p-value, but an F-score if it's N-to-C or C-to-N. And it handles it in either direction. Now, if we wanted to, maybe instead of sorting by R, although we don't have, we have different effect size measures depending on the data type, and they're not really comparable. You can't compare an R to an F. The only thing we really could compare would be the p-value across all of them. Let's go ahead and do that. I'm just going to change this to sort values by P instead of R. There we go. Probably want to do this. Ascending equals true in the case of p-values because smaller means more reliable. All right, so age, again, let's not overinterpret. We can't say that age is the most important variable because we can't compare R to smoker, but we can say that age is the most reliable. The coefficient here is the most likely to get that same or something close to that again if we were to collect more data of all the features. Down here, we're still going to get an error because, oh, actually, no, not on salary because we don't have C-to-C relationships yet. So let's take a look at this. We got some warnings. Let's see. This is new. Every time they update their packages, things change a little bit. F1 requires at least 1 input. Oh, we're getting this warning because we have some missing data issues. So let's not worry about those. What we are getting here is the p-value for all the numerics. But now, for things like position and team, we're getting F-scores, which is good. Player name and field goal percentage has some, all these have blank data, but player name and player additional, that's what gave us the warnings. The reason why we have those problems is because each value is unique. We can't have these situations where it's basically adding a list of players' salaries right here in this fstats one way, a list of 1 for each player name right there. And it's saying, wait, all arrays have a length of 1, meaning you've only got 1 value each. You've got to have at least 1 input that has more than 1 value. So we just need to add some cleaning here at some point to tell it to ignore those types of features. All right, so next, all right, well, let's go ahead and handle this missing data issue. I think this is a good time to do this. Normally, I like to keep my cleaning functions separate from my EDA functions, but in this case, it prevents us from getting clean data and good, useful values. I just want to tell it what to do when there is missing data. So I think the way I want to handle that is let's calculate the amount of missing data and indicate it in this table. And then when we run these analyses for things like team and position, or in this case, all these down here, these values, let's remove the missing data so that we can still calculate these metrics down here. And then just indicate that, hey, by the way, there was some missing data in these fields. So here's how we'll do that. Let's come back to our function and let's start by calculating missing data. That applies to everything. So do I want to do it? Yeah, I want to do it for every feature. So it'll go inside the loop. Do I want to do it if the feature equals a label? No, I don't want to. I don't want to do it for the label against itself, so it'll be inside here. Do I want to do this for any type of relationship? End to end, C to N, C to C? Yeah, I think I do. So that means it's going to go right here. And I'm going to calculate a missing value. So to do that, first of all, I'm going to need to make well, let's calculate missing here, a variable, and I'm going to set this equal to the df.shape and shape 0. That returns the number of rows in the data frame. And I want to, if I want to get I guess first what I need to do is calculate a temporary data frame that has no missing data. So to make this simple, I'm going to make a temporary data frame out of just the feature and the label, because I only want to remove the rows where either the feature or the label are missing. And so to do that, I can filter a data frame like this that says set dftemp equal to another version of the data frame that has only these two features in there. And in fact, I may even want to run copy on that just to avoid memory issues. We'll check and see if that works. Next, I want to drop all rows from just this temporary data frame that only has these. So dftemp drop na. I'm pretty sure, can I call in place in that one? In place, no. No, it won't let me do it. So all I'll have to do is say dftemp equals dftemp.drop na. And let's see if copy will work on that too, to avoid memory issues. So drop na will remove any row where either one of these values is missing. So now I have a slightly smaller version of the data frame. And just to show you what I mean, let's run this. I'm going to print two things. I'm going to print df.shape and then dftemp.shape. So you can see what we're getting. And I'll comment this out. I'm going to run that real quick and just make sure that my copy feature here works as well. I'm not going to run it on insurance because I know there's no missing data, but I'm going to run it on salary here. All right, so here's what we got. For each column, it printed out both versions. So the original and the reduced version both had 467 rows. That's because there was no missing data. Well, as soon as we come down to here, this one had one row with missing data in it. In fact, let's print out the column that we're on. So it'll print that out as well. Oops, I didn't even do that one. This one. Okay. All right, unnamed player. Here we go. Field goal percentage. So one of the rows in there was missing, and we can see that's why down below, field goal percentage was one of those that we couldn't calculate any of the end-to-end statistics for. So what I want to do is calculate the percent of data missing so that we can record it in the table. And I think I'm going to put it right up front here at the very beginning of the table. Missing percent. And now I'm going to calculate that missing percentage right here. So I'm going to say missing percent is going to equal the original data frame shape 0. That's going to return back just the number of rows, minus the temp data frame dot shape 0. So on that first one, for field goal percentage, this is going to return a 1 divided by the original dot shape 0. So it'll give it to us as a percent. And I think I'm going to go ahead and run round on this whole thing to however many decimals we wanted to round to. Yep, that'll work. All right, so we've got a missing percentage, and now I've got to remember to add this so that my rows match up into each one of my control flows. So right here, let's start an end-to-end. I'm going to add missing. Add it to C to C, and then down here, add it to N to C, C to N. All right, let's see if that works. Perfect, we've got our missing data percentage right there. We know there was none in insurance, but in this one, all right, now we get, I guess technically it's not a percent, it's a proportion because I haven't put it in percent form. So why don't I go ahead and multiply this by 100 and add the percent sign after. So let's do that. Back up in our function. I'm going to multiply by 100. And then when I add it in here, I guess I can put it in an F string. Missing percent. Oops, not that percent. There we go. So now that'll put in the missing value. So let me replace each of my spots here with that same thing. There we go. Now I got it in a percentage. Cool. Now I have a version of the data frame that doesn't have any missing data. So I only want to use this. Well, really, I could use this the rest of the way through, because if there was no missing data, it won't. It'll just use the original version. So I'm going to copy this data frame into the rest of my processes here. So in particular, I'm going to highlight DF because then it highlights all the places in collab where it finds DF. So I'm going to replace df.shape inside each of my if and else blocks. So right here, this is going to be df temp, temp, down here, temp, in each of these spots as well. All right, if I've found all of them, then what we should get is working numbers now. All right, check it out. We no longer have like fill goal percentage, it's now working. However, it notates that, by the way, some of the data was missing, so just be aware that this is based on the data that wasn't missing, the data that was there. So that cleans up our results a bit. It's still working here for the C to N relationships. All we have left is this issue with 2, where we had an equal number of categorical values as there were total number of rows. Let's go ahead and handle that issue at the same time right now. So the way I want to do that is, let's just decide on, I'd almost like to give a warning if there's too many possible values. You know what? I think I'll save that part for the end. Instead, what I want to do now, I'm going to call it good enough for now. Let's go ahead and fill in. We still need to handle C to C relationships. So down here in the airline satisfaction data, we haven't visited this one in a while. We can't run it on this one because we sorted by p-value. Once again, I'm going to take that one off just so you can see this work. Return output df. Okay, so for this one, we're comparing satisfaction, which was a categorical feature of either satisfied or not satisfied, with each of these features right here. And it worked every time the feature was numeric because our function handles numeric to categorical features with f-scores. And we've got all these p-values. Wow, every single thing here seems to make a difference. What we don't have, though, is here under gender, customer type, type of travel class. These are categorical features. We need to calculate a chi-square statistic, Pearson chi-square statistics for those. So let's go back up here to our function, and this one's a lot easier. We did the hardest one right here. This last one will be pretty quick and easy. For chi-square, I'm not going to explain the details behind this. I'm going to assume that you've already learned it in another spot in the book, or you're able to go online and understand a chi-square. First thing you have to do is create a contingency table. So I'm going to make just a variable called contingency table, I guess. And that's going to be, we use the pandas crosstab function to do that. So this is just a count of the number of times each pair exists. So the number of times satisfied people were, I think customer type is loyalty. Here it is. So it's the number of instances where a row was satisfied and female versus satisfied and male, or not satisfied and female, not satisfied as male. You know, and it does that with each pair of categorical features. It just comes up with a table of a count of the number of times each pair of values comes up in the data set. And that's what this contingency table is right here. So the way we create that is we simply pass in df temp the feature we're currently on, df temp the label we're currently on. Once we have the contingency table, calculating a chi-square statistic is pretty easy. We're just going to use the stats package again from SciPy. and it's going to output 4 values: the chi-squared, which is x2, a p-value, a degrees of freedom, and an expectancy table. Let's call it expected. That'll work, expected. And we'll call the stats package dot chi2 contingency, and we'll pass into that the contingency table we made above. There we go. Once we have those statistics, we're just going to plug them in. And really from this one, all I'm going to keep is the chi-squared and the p-value. So I better make a new column up here for chi-square. And that means I've got to add a path. Now that I have a new column, I've got to add a value in each one of my paths here. So here at the very end of num to num relationships, I'm just going to put a dash, just like I did for the F score right there. Down here in the contingency table, I'm going to put the actual x squared. And now that I have a p-value, I can replace this one with the p-value, which means I can go back down here at the bottom to allowing it to sort by p-value again. Lastly, in my C to N, N to C relationships, I've got to add another dash for chi-squared. Okay, let's go ahead and run that. There we go. I have a chi-squared statistic now for each of my C to C relationships. I have an overall table, which is pretty awesome, that gives me a list of every bivariate relationship, the appropriate measure of effect size automatically based on the type of data of the feature and the label, and a p-value. And it works pretty well. I think I've hit an hour, so I'm going to stop this video right here, but I'm going to make some improvements on this and make a part 2, because I still want to clean up these features where I've got, and where did they go in here? Oh, I just got to scroll down. Where I've got too many possible group values, and then I'd also like to add visualizations to this as well. But we'll stop this one for now.